AI Liquid Neural Networks Deep Dive: How Senior Engineers Master Continuous Time Dynamic Models in Modern AI Systems. Episode 90. Welcome back to Agentic AI World, the daily interview prep series for engineers who want to stand out in AI roles. I'm your host, and today we're going deep on liquid neural networks, one of the most underrated architectures in modern AI. Part 1. What are liquid neural networks? Liquid neural networks were introduced by researchers at MIT in 2020, specifically the MIT SAIL group led by Ramin Hassani. The name comes from liquid state machines, a concept from computational neuroscience. Here's the core idea. Most neural networks are static. You train them, freeze the weights, and the network behaves the same way regardless of when or how you use it. The computation happens at discrete time steps. Liquid neural networks are different. They're built on ordinary differential equations, ODEs. The neuron activations don't just update at discrete steps. They evolve continuously in time. The network is literally flowing, adapting its internal dynamics based on the history of its inputs. Think of it this way. A traditional RNN neuron asks, what is the input now, and what was my hidden state last step? A liquid neural network neuron asks, how is the input changing over time, and how does that drive the continuous evolution of my state? This is not just a philosophical difference. It has enormous practical consequences, especially for time series problems, robotics, and autonomous systems. Part 2. The math behind it. Let's look at the core equation. The state of a liquid neuron X at time t is governed by tau times dx over dt equals negative x plus f of input, where tau is a time constant. It controls how quickly the neuron responds to changes. F is a nonlinear activation function, and x is the current neuron state. This is a first-order linear ODE with a forcing function. Crucially, tau can itself be a learned function of the input. This is what makes the system liquid. The time constant adapts. When the input is changing fast, the neuron responds quickly. When things are stable, the neuron holds its state longer. The solution to this ODE gives you the neuron state at any point in time, not just at fixed intervals. This is continuous time computation. In practice, you discretize using a numerical ODE solver, but the underlying dynamics are continuous, and the solver can take variable step sizes to track the signal accurately. Part 3. Neural circuit policies. The most powerful application of liquid neural networks is in what the MIT team called neural circuit policies, or NCPs. An NCP is a liquid neural network that's structured to mimic the neural circuits of small organisms. Specifically, they took inspiration from the nematode worm C. elegans, which has exactly 302 neurons, fully mapped. The key insight: you don't need a million parameters to solve hard control problems. You need the right wiring. A carefully designed circuit of 19 liquid neurons, connected in a biologically inspired sparse pattern, was able to drive a car autonomously in simulation. Let that sink in. 19 neurons. Not 19 layers. 19 neurons total, outperforming much larger networks on certain tasks. Why? Because the architecture encodes structural inductive biases. The neurons are wired as sensory neurons, interneurons, motor neurons. Information flows in a biologically motivated direction. The liquid dynamics handle temporal integration naturally. Part 4. Closed-form continuous time networks. In 2021, the same MIT group published an improvement, closed-form continuous time networks, CFC networks. The original liquid networks required a numerical ODE solver at each time step, which is computationally expensive. CFC networks derive a closed-form approximation to the ODE solution, so you get the benefits of continuous time dynamics without the solver overhead. The CFC cell computes the hidden state using an explicit formula. H at time t equals the ODE solution approximated as a sigmoid-weighted combination of two learned functions. This makes CFC networks competitive with state-of-the-art sequence models in terms of training speed, while still preserving the expressivity and temporal dynamics of the liquid formulation. CFC networks have been shown to outperform LSTMs, GRUs, and standard transformers on certain time series benchmarks, with far fewer parameters. Part 5. Advantages over transformers for time series. Here's the comparison that interviewers love to ask about. Transformer advantage: global attention, massive parallelism during training, excellent for discrete sequence tasks like language. Liquid/CFC advantage: native continuous time modeling, handles irregular sampling naturally, excellent interpretability, low parameter count, causal by construction. The critical difference is a regular time series. Most real-world sensor data, medical, financial, IoT, is not sampled at regular intervals. A patient's heart rate isn't measured every millisecond. A financial event doesn't happen every second. Transformers need you to either resample to a fixed grid or use positional encodings that struggle with irregular gaps. Liquid networks handle irregular time naturally. The ODE integrates over whatever gap exists between observations. This is a massive advantage in healthcare AI, autonomous robotics, and industrial IoT, all hot areas for senior AI engineering roles. Part 6. Interpretability. Another killer feature. Liquid neural networks with NCP wiring are highly interpretable. Because you have a small number of neurons with explicit roles, sensory, motor, you can visualize which neurons activate in response to which inputs. You can actually see the network's reasoning. The MIT team showed that you could identify specific neurons responsible for specific decisions in the car driving NCP. You could ablate a single neuron and predict what would break. This is almost impossible with large transformers or deep CNNs. For regulated industries, medical AI, autonomous vehicles, financial AI, this interpretability is not just nice to have. It's a regulatory requirement. Liquid networks offer a path to certifiable AI. Part 7. Interview angles. Let's drill the interview questions. Question 1. What problem do liquid neural networks solve that LSTMs don't? Your answer. LSTMs process sequences at fixed discrete time steps. They can't natively handle irregular sampling. You have to resample or add masking. Liquid networks model time as a continuous variable via ODEs, so irregular gaps between observations are handled exactly, without information loss or distortion. Question 2. How would you use a liquid network in production? Your answer. For a time series prediction task with irregular sampling, like patient vital signs, I'd use a CFC cell as the sequence encoder. CFC gives me continuous time dynamics with a closed form update, so no ODE solver overhead at inference. I'd pair it with a standard MLP decoder for the output head. Training is standard backprop through time. The CFC cell is differentiable. Deployment is just a forward pass, same as any RNN cell. Question 3. What are the limitations? Your answer. 3 main limitations. First, for purely discrete sequence tasks like text, transformers are generally better. There's no temporal gap to exploit. Second, the NCP wiring requires domain expertise to design. You need to know how to structure the sparse connectivity. Third, CFC is an approximation. For very high-frequency dynamics, the approximation error can accumulate. Question 4. Why would you choose a 19-neuron NCP over a deep network for robotics? Your answer. Because interpretability and sample efficiency matter more than raw capacity in safety-critical systems. A 19-neuron NCP trained on driving data produces a system you can audit. Specific neurons have specific functions, failures are diagnosable, and the model can be certified. A 10 million parameter deep network is a black box that lawyers and regulators can't approve. Part 8. Where liquid networks are going. The trajectory is exciting. 3 developments to watch. 1. Liquid transformers. Researchers are exploring hybrid architectures that use liquid dynamics for the temporal encoding layer, then transformer attention for global mixing. Early results are promising for long-horizon time series forecasting. 2. On-device robotics. Liquid NCPs are being deployed on small microcontrollers for drone navigation and robotic manipulation. Their tiny parameter count makes them ideal for edge inference where you have kilobytes, not gigabytes, of memory. 3. Neuroscience-informed scaling. The C. Elegans wiring was just 302 neurons. The human brain has 86 billion. Researchers are exploring how to scale NCP-style architectures using higher organism neural circuit blueprints, potentially unlocking qualitatively new capabilities. Wrap up. Let's summarize episode 90. Liquid neural networks are continuous time recurrent networks governed by ODEs. The time constant adapts to the input, making the network liquid. Neural circuit policies apply sparse, biologically motivated wiring to achieve remarkable efficiency. 19 neurons driving a car. Closed-form continuous time networks give you the same dynamics without the ODE solver overhead. The killer applications are irregular time series, robotics, and interpretable AI in regulated industries. If an interviewer asks you about time series modeling and you can drop CFC network and continuous time ODE dynamics and explain why it beats in LSTM on irregular data. You're in the top 5% of candidates in the room. That's episode 90. Keep building, keep learning. See you tomorrow.